Okay, so here we have another problem. We have a 50-gram ball is launched straight up by a spring of a spring constant 10 newtons per meter. The spring is initially compressed downwards a distance of 50 centimeters until it is from its equilibrium position, and then it releases to launch the ball upward. So we want to use energy considerations to find the launch speed of the ball, which occurs when the spring arrives back at equilibrium. Then what we want to do is we want to use the energy considerations to find the maximum height that the ball reaches. Okay, so let's draw a quick picture to kind of understand what's happening. So again, here's our surface, and I'm going to kind of break this up into before and after because I think that's important. So we're going to say before, and this is going to be after. Actually, you know what? I'm going to change those terms so we can match this to our equation. This is going to be initial and this is going to be final. So what we have is we have a spring. Here's my very crooked looking spring. And initially what happens is that this spring is compressed. So it may be initially at equilibrium, initially is like this. So if we think of it like that, it's compressed a certain amount. And so it's compressed, and on top of it, maybe on a surface, but there is a ball. So we have a ball on top of it. And then what happens is that the spring then releases. So maybe something like this. And of course, I'm not the best artist, but that's okay. And here's our ball again. Here's our surface. This is running out of space. Let's say here's my ball. My ball, for some reason, got smaller. But we have a couple different important ideas. So when we are thinking about our energy considerations, what we really want to be thinking about is our conservation of mechanical energy. So what we have is we have mechanical energy initial is equal to our mechanical energy final. And remember, we have several different types of energy, and I'm going to use some abbreviation. So Ki, so it's going to be my kinetic energy initial, is going to be equal to my Ug, which is my gravitational potential energy. And then, of course, Us for my spring constant. Let me go ahead and put I's here so we remember our I's. This is equal to Kf plus Ugf plus USF. So we have these ideas. So what we want to be thinking about is what type of energy do we have before and after? So let's think about that. Let's start canceling some stuff out. So initially, we don't have any kinetic energy because the ball is not moving. Okay, so we can cancel that out. Now, if we set this level to 0, we could also say that it has no gravitational potential energy. What it does have is energy from the spring because the spring is compressed. So we do have that. So if I were to write this down, I'm going to go ahead and kind of write down this now that I have that for my equation. So I have 1/2 kxi squared. Okay, now let's cancel out some more. Okay, so do we have kinetic energy? Yes, because the ball is moving up. So we do have kinetic energy. Do we have gravitational potential energy? Yes, because the ball is above that 0 position. So we do have this. Do we have our spring? And that is a no. We do not have our spring because, first of all, the ball is no longer connected to the spring because we're thinking about the ball. But the other thing that we want to be thinking about is that when the spring is at equilibrium, there is no force being applied by the spring. So this is actually 0. So if we were to now plug these in, we have 1/2 mv final squared plus mgh. And so what we are trying to find in this equation is we are trying to find our velocity final again. So we want to know what is this value. So let's go ahead and plug in things to our equation. So we have 1/2. We know our K value. We were told that was 10 newtons per meter. We know the distance that the spring was compressed, what we do want to do is we do want to change our centimeters into meters. So this is actually going to be 0.15 meters. And that's going to be squared. This is going to be equal to 1/2. The mass of our ball, again, changing this to kilograms, be 0.5 kilograms times our velocity final squared, which is what we're trying to solve for, plus, again, the mass of the ball times our force due to gravity, 9.8 meters per second squared, times our height, which we know when we let go, so we're thinking about right when it launches off, it's 0.5. Let me erase this. Let me see if I can make myself a little bit more room. So meters per second squared, and this is going to be 0.15 meters. Okay. So we are trying to find our velocity final, making sure that we remember that it is v final squared. So what we want to do is that we want to rearrange our equation. And if we do that, we will get our velocity final is equal to 1.25 meters per second. So what we see is that all that potential energy that was held into the spring not only went to gravitational potential energy, but it also went to our kinetic energy. So we can see that that amount of energy stored in the spring was converted to two different types of energy. Okay, so let's go ahead and think about part B. So we have used energy considerations to find the maximum height the ball reaches above the launch position. Okay, so we're talking about this. So we want to know, okay, so we're starting right here. Let me kind of draw this over. Oh no, I didn't want that color. Okay, let's do this. Okay, so let's say that we're starting right here. We want to know what is the height. So let's say that this is our height. So we want to know how high does it go from that position. So it says specifically to think about energy considerations. So what that means is that we want to think about our mechanical and potential energy. So our mechanical initial and final. So thinking about this, and if we're talking about when it leaves that the platform or the spring, and we're talking about that as a height, what we are thinking about now is that at that point, we have kinetic energy initial only, 1/2 mv squared. And we know what that is. So we're saying that this is now our initial, and that's all converted into potential energy. And we're talking about the highest. And remember, at the highest point, our velocity is 0. So we have no kinetic energy. So what we're talking about is how much of this velocity, how much of this kinetic energy, or how does this kinetic energy transform into potential energy? And so how much of that energy is going to go to the height? So this is going to be our equation. One of the nice things about this equation is that since mass is on all sides, we can cancel it out. We could not cancel it up in the previous problem because our spring constant does not depend on the mass. So if the mass was involved in that equation, then we could have, but since it's not, we can't get rid of that. So let's go ahead and plug in our variables. We have 1/2. This is going to be our velocity, which we know is 1.25 meters per second squared, and this is going to be equal to 9.8 meters per second times h, and we're trying to figure out what h is. So once you rearrange that problem and you solve for h, what you end up getting is your height is going to be equal to 8 centimeters. So